Alright, so we are going to take a look here at matrix elimination and the matrix elimination process. And matrix elimination is the process that we use when we want to solve the linear system of equations A times X is equal to B. And I'll demonstrate the process with some examples. So first, let's look at a linear system here, a system of three equations. Okay, so here we have a system of three equations and three unknowns. And the first thing I'll do is I'm going to write the system in the matrix form. And in order to do that, I'm going to take the coefficients of the unknowns from the left-hand side of the equation and put them into a matrix. And this matrix will multiply a column vector that contains the unknowns. And then on the right-hand side, we'll have another column vector that contains the elements from the right-hand side of the system. Okay, so these two representations mean exactly the same thing. After we write this in the matrix form, we're going to form the augmented matrix. This is the first step of elimination. So I form the augmented matrix by writing my A matrix. And now I'm going to augment it with the vector B. And this is where I start my elimination. Notice that I have a pivot in the 1, 1 position, and I'm going to use that pivot to eliminate the elements underneath of it. So let's get started. In this first step, my top row is not going to change. I'll form the new second row by subtracting twice the first row from the second row. So let's just make a note of that here. R2 is going to R2 minus twice R1. And when I do that, I'll get a 0 here. 2 minus 2. In the next position, I have 5 minus 4 gives me 1. And in the third position in the second row, I have minus 4 minus negative 2, which gives me minus 4 plus 2, or negative 2. And then on the right-hand side, I have 5 minus 6, which gives me negative 1. My next step, again using my first pivot, I will eliminate the position in the third row, first column. So here row 3 is going to go to row 3 minus twice row 1. I'm sorry, minus 3 times R1. There we go. That'll give us a 0 in the 3, 1 position. In the next position, we're going to have 4 minus 6, negative 2. Then we'll have 2 minus negative 3, which gives us 2 plus 3, 5. and 12 minus 9, which gives us 3. My next step, I will use my second pivot to eliminate the position beneath it. Again, my first row isn't changing. And my second row will not change in this step either. In the third row, I'm going to add twice the second row to the third row. That will give me a 0 in this position, and also a 0 in the 3-2 position. In the 3-3 position, I will have 5 plus -4, which gives me 1. And on the right-hand side, I will have 3 plus -2, which gives me 1. Okay, at this point, note that we have 3 pivots. And also that the left-hand side, everything to the left-hand side of the dotted line, is a matrix where everything below the main diagonal is 0. Now I can write my system again. And note that the first equation, the first row, has not changed, and therefore the first equation is not changed. However, the second row has changed. So my new second equation, y minus 2z, is equal to -1. And the third row is also changed. My third equation is equal to z equals 1. So I can now easily solve this system. I have my answer for z equals 1. I'll perform back propagation and write the second equation, plugging in the value for z. And this gives me y equals 1. And I'll perform back propagation once again, plugging in this time the values for y and z into the first equation. And I get my solution for x. Okay. Let's look at another equation, another system. This time, we have 2x plus y minus 3z equal to 1. 5x plus 2y minus 6z equal to 5. And my final equation, 3x minus y minus 4z equal to 7. So following the process again, I'm going to write this in the matrix form. I form my A matrix. Again, using the coefficients of the unknowns on the left-hand side of the equation. Matrix A gets multiplied by a vector that contains the unknowns, and this yields the column vector solution, the elements of which are on the right-hand side of my original system. I'll form the augmented matrix. And now I can begin my elimination. Now in this case, I'm going to have to form the new row 2 by taking twice row 2 and subtracting from that 5 times row 1. That'll give me a 0 in the 2-1 position. In the 2-2 position, I will have 4 minus 5, which gives me minus 1. And in the 2-3 position, I will have minus 12 minus negative 15, which gives me minus 12 plus 15, giving me 3. On the right-hand side, I will have 10 minus 5, which gives me 5. I'll use this pivot once again to eliminate the third row first column. So in this case, row 3 is going to transform to twice row 3 minus 3 times row 1. That'll give me a 0. Here I will have negative 2 minus 3, negative 5. In the 3-3 position, negative 8 minus negative 9, which is negative 8 plus 9, which gives me 1. On the right-hand side, 14 minus 3, 11. Okay. I'll continue the elimination. Second row is not going to change. I'll form row 3. Remembering that I want to use this pivot to eliminate this 5. So row 3 will go to row 3 minus 5 row 2. I'll maintain a 0 in the 3-1 position. I'll also get a 0 in the 3-2 position. And now I have 1 minus 15, negative 14. And on the left-hand side of the equation, I have 11 minus 25, which gives me negative 14. Okay. At this point, notice that I have 3 pivots. My last one being the negative 14 in the 3-3 position. That counts as a pivot. And I can now rewrite the system of equations. My first equation, again, has not changed. My second equation, minus y plus 3z equal to 5. And my final equation, negative 14z equals negative 14. Also notice again that the A matrix that formed the left-hand side of the augmented matrix is now in the upper triangular form. From the bottom equation, I see that z is equal to 1. Using back propagation, I form the equation minus y plus 3, plugging in the value for z1 is equal to 5. This simplifies to minus y equals 2, so y is equal to negative 2. Once again, using back propagation with my top equation, I plug in the value for y. and the value for z. And I find x equal to 3. Let's talk about the key points of this process, the matrix elimination process. First of all, we start with a linear system and we write the system in the matrix form. Next, we form the augmented matrix. Then we actually perform the row operations. The goal is to transform A into the upper triangular matrix U. Once we've done that, we perform backpropagation. The goal here is to find the values of the unknowns.